Thank you very much for having me. So I will be presenting this project that was sponsored by Keynes Fund. The title of the project is High Dimensional Cointegration. It is a joint project with Chen Wang, who used to be a postdoctoral INET student here at Cambridge, but now is assistant professor of statistics at University of Hong Kong. We would like to thank Keynes Fund very much for funding, because it helped us a lot to achieve our goals much more efficiently. What were our goals? The main goal was to better understand the phenomenon of cointegration in high-dimensional data. And so when you think about high-dimensional data, and I will be writing here, high-dimensional data, then these days people very often associate high-dimensional data with factor models. So then you would think about high-dimensional factor model. And so we are no exception. So when we decided to think about this high-dimensional cointegration, we also thought about factor model. But since our interest in cointegration, so we don't just have high-dimensional data, but we have high-dimensional non-stationary data. Non-stationary. Well, when you talk about non-stationary data, very often people model it still using factor model with a few non-stationary factors, plus stationary noise. There are a lot of models like this. And these models will imply cointegration big time. Cointegration. Why is that? Well, because see, our factor model contains just a few of factors. They are non-stationary. They can be understood as common trends in the data, common stochastic trends in the data, but everything else is actually stationary. These are errors are stationary. So there are a lot of cointegrating relationship in this data. And well, the first question that we ask ourselves, is this a good model? Good model. And we looked at what people, like how people defend this, this kind of model. And there are two quite obvious arguments in favor of this model. The first one goes like this. A few factors indeed explain a lot of variation in the data. A lot. So when I'm saying a lot, this is really a lot. Almost all variation in the data is explained by, very often, say by 5 or 4 factors. So the second thing is that, well, residuals after extracting factors look stationary. And by this, I mean the following fact. Suppose that you extract factors from your data and then look at residuals and test each of these residuals for each series, do Dickey-Fuller test for unit root. And then you will reject overwhelmingly unit root in these residuals. They do look stationary. So people very often say, yeah, this is a good model for high-dimensional non-stationary data, and very often use it, for example, in macroeconomics. So we wanted to better understand this argument, and we found out that actually all this nice picture is kind of easily destroyed. I'm trying to depict hammer here. So the nice picture is completely destroyed by the following thing, which we call spurious factor. Spurious factor. Or spurious factor analysis. And well, the big portion of our project was was to document the spurious factor phenomenon and argue that it appears very, very often in various theoretical and empirical studies of high-dimensional non-stationary data. So let me talk a little bit, explain to you what this spurious factor phenomenon. Well, and just to explain this, I would like to give you an illustration really. It's not very, very general illustration. It's supposed to be very simple illustration. So in this simple illustration, I will consider the following data. The data have two indices, I and T. I is cross-sectional index, T is temporal index. And the data is actually pure random walk. So today, data is equal to yesterday's data plus completely independent things, epsilon IT. And I will even assume that epsilon IT are IID mean 0, variance 1, and I also will need the finite fourth moment, but nothing else. So this really is implying that there is no factors in the data because the data cross-sectionally is totally independent. See, there is no commonality across different eyes. So each of this data corresponding to different eyes is just a random walk, absolutely independent. Okay, so nevertheless, we can do factor analysis with this data. We don't know whether there is factor or not there. Well, and to do this factor analysis, you usually do principal components analysis. What is this principal components analysis? First, you combine the data in a matrix. So this matrix consists of all this xit, I going from 1 to capital N, T going from 1 to capital T. There are T time period in your data and large N cross-sectional units. Then you form matrix X minus X bar prime X minus X bar. So what is this X bar? This is simply average over time of your data. So you average over time your data and subtract this average from the data. And then you transpose this matrix, multiply by itself, and take eigenvectors and eigenvalues. Compute eigenvalues and eigenvectors. So let's call the kth eigenvalue lambda k hat. I'm putting hat because this is estimated from the data. And the kth eigenvector is f k hat. So this are eigenvalue and eigenvector. And the first one will correspond to the largest eigenvalue and the most strong factor. The second one will correspond to the second largest and the second strongest factor, et cetera, et cetera. So of course, there is no factors in the data. So you might think that, well, this will be something kind of not very significant, not very large. It turns out that the picture is totally different. You will see very, very big values of eigenvalues, even for this independent data. You will see some well-structured factors, and you might misinterpret this picture as saying that there are few trends in the data that explain a lot of variation. So let me be more precise here and formulate a theorem. So I will formulate the following theorem. So to formulate the theorem, I will first describe some deterministic vector. So I will call this deterministic vector dk. It is t-dimensional vector, so it's d1k, d2k, etc., dtk. Remember, our data has t time periods, and estimated factors will also have t components. But this is deterministic vector defined in particular way. Specifically, the component t of this vector is proportional to cosine. Cosine of t by like this, divided by capital T. Okay, so this k can be 1, 2, 3, or etc. And as I say, t-dimensional vector, and this is just a cosine. So here is the theorem. Theorem is like this. There are two parts in this theorem. First, consider your estimated factor, and this is kth estimated factor. If k is equal to 1, this is the strongest factor in your data. And take scalar product with this vector, deterministic vector. So it turns out that this converges in probability to 1. Okay. And the second thing is saying that if you take the eigenvalue and divide by sum of all the eigenvalues, then this converges in probability to 6 over k pi squared. So what does this tell us? So this basically tells us that factors, quote unquote factors, because there are no factors really in this data, look like cosine waves. Okay. Indeed, well, this factor becomes asymptotically collinear to this vector that I described here. And this vector is simply kind of cosine wave vector. And this fact saying, well, what is this ratio? This ratio describing a portion of variation explained, quote unquote, by the factor. So portion of variation explained. So look at this number here. Suppose that we are talking about first factor, quote unquote. So then k is equal to 1. And pi is just pi, 3.14, right? Something like this. So squared, you will get around 10 in the denominator. So 6 divided by 10 will be 0.6. What this tells me? This tells me that even if you have absolutely independent data without no factors whatsoever, the first factor will explain 60% of variation in this data. And you can go further, like put here k equal to 2, 3, and compute according to this formula, what is the percentage of variation explained in the data. And remember, my data is independent cross-sectionally. There are no commonalities here. Okay, so let me just illustrate briefly this cosine vector. So what they are. So they look like this. So here on the horizontal axis, so I just normalized time. Time now is going from 0 to 1. But in principle, I will have capital T time periods here. And I also normalize the size of this, well, the magnitude of this wave. So the first kind of cosine wave looks like a linear trend, really. The second looks like a quadratic trend. And the third looks like cubic, etc. So these are kind of, if you'd like, trigonometric versions of trends. And how about the eigenvalues? Remember, eigenvalues representing the strength of the factors. So here I normalize them that the largest eigenvalue is 1, the second largest is 2, etc. So this is how eigenvalues will look like for this totally independent data. And this kind of pictures are very often used in empirical research. It is called scree plot. So people just looking at this picture and say, oh, see, one eigenvalue is really much larger than the rest. I think that there is one factor in the data. Oh, well, maybe two, because the second one is also kind of separated from this. And if you really use some criteria like Binang information criterion to determine the number of factors in this data, you will very often find that there are either one or two factors in the data. And remember, this data does not have any factors whatsoever. So all this phenomenon we call spurious factor phenomenon. And it turns out that it is very, very general in the following sense. So I described to you theorem for completely independent data, but even if you will consider data like this, so it's x1, t, etc., x and t, like vector of data. And then you will consider xt is equal to xt minus 1, and then plus some matrix lag polynomial times epsilon t. And this matrix lag polynomial can be very, very complicated polynomial, okay, n by n polynomial. Well, as long as this polynomial cannot be as long as psi1 cannot be well approximated by small rank is not equal to small rank matrix, as long as this holds, basically, the previous theorem that I showed you holds for this data. And this is really very general model. Moreover, we extended our analysis to not just to unit roots, but to local to unit roots, and all kind of different data, mixing unit root data with stationary data. So it turns out that the basic phenomenon, spurious factor phenomenon, remains intact. Does it matter empirically? Yep. So let me show you one picture. So here is the picture taken from Jushan's by-analysis of sectoral employment data in United States. So he considered about 60 different sectors in United States. And this data is from about 1948 up to 2000. So what you see here, like this cross sections are simply, well, time series for different logs of employment in different sectors in the United States. So as you see, this is very non-stationary data. There are trends in each of this employment, log employment. So what Jushan Bai did, he took this data and did principal components analysis, and then used the factors extracted from this data to, well, say something about just employment, et cetera, et cetera. So like about many macroeconomic things in US economy. So the question, is his analysis spurious or not? How do I know? Well, one way to check is to look actually at the estimates of the factors. How do they look like? Do they look like cosine waves or not? So here is how his factor look like. So this is the first factor. It looks terribly like linear trend. This one is the second factor. It looks very much like what quadratic trend. And this is this third factor. It looks like the cubic trend, right? Just as I told you, these cosine waves look like. So this is a indication that something is wrong with analysis, and you cannot really trust this kind of analysis. Well, can you do more formal tests? Probably yes. We are working on more formal tests, which are based on this idea that you can extract factors from the level data, or you can extract factors from the data which is first differenced, but then you accumulate these factors back. And you can compare the two ways how you extracted factors, whether they look the same or different. If they look different, it's bad. And we are developing tests based on the amount of the difference, but this is still in progress. So that basically is what I have to say.